we started chapter 8, estimation of parameters and fitting of probability distributions. So here, the motivation is that often you have some data that you want to model using a probability distribution. A probability distribution is often parametric, and it comes with certain parameters, which then you need to estimate based on your data what those parameters are. And then you need to test how good your estimator is doing some kind of goodness of fit. So that sort of circle of ideas is the content of chapter 8 and 9. And in section 8.1, 8.2, we do an example with alpha particle decay. So this is modeled as a Poisson process. And a Poisson process has three things going for it. One is that the Poisson, so for each time interval that we have, each 10-second time interval, we have a constant rate of decay, that these time intervals are independent of one another, and that alpha particles can't be simultaneous. They don't coincide with one another. So these are all realistic assumptions to make, and so this is a Poisson process. The next question is what's your parameter going to be? So a natural estimate for the parameter is the total number of arrivals over the total number of intervals that we have, which is 8.4 arrivals per 10 seconds. And that's what we're going to use. So in the book here, they show this table, which gives your data. In the second column here is the number of observed intervals out of the 1,207 10-second intervals that contain a certain number of hits. So, for example, 28 out of 1,207 10-second intervals have 3 hits. So you can ask yourself then, how many would you expect if the model is correct? And that's a calculation that we're about to do. So the key idea here is that each of these intervals is independent, and so, for example, each interval, if you define it as being successful by getting 3 hits, then you can compute the probability P that an interval has 3 hits. And that calculation is just given here, right? Because the probability that your interval has k hits is given by this formula for a Poisson random variable. In this case, we use 8.4 for lambda. So when x is 3, we get 0.022 for your p. So the number of intervals that you would expect, having 3 hits is binomial. So this is binomial. So we have this many intervals, and this is the probability for success, right? And so the number expected here is the expectation of this random variable, which is NP. So this is just 1207 times 0.022. And you would do that for each different n here by computing a different probability. We then can test. We have then a column for expected, a column for observed, and we can assess how good that fit is using a chi-square test that we'll do in Chapter 9. We then soldiered on to our first estimator, which is called MOM, method of moments. We reviewed a gamma distribution and noted that a gamma distribution has two parameters, both the rth particle r. Oh, okay, let me backtrack a bit. So a gamma distribution, it's a waiting time till your rth alpha particle arrives. And so you have two parameters, r being your rth particle and lambda being the rate that particles are arriving for each interval. Some standard stuff about what the density of a gamma distribution is and what the expectation and variance are. And then, so I am prescribing here a method to compute the method of moment estimators if your distribution has, say, L parameters. Step 1 is you compute the first L moments. This is going to give you L, a system of L equations. So a moment is the expectation of a power of x. How do you compute something like this? Well, you can just use the definition of expectation. That's a terrible way to do it, but that can be done. And a better way to do it is using a moment generating functions, which is section 4.5 in Rice. I'm not sure whether we're going to get to that or not, but that's sort of the main tool for computing these types of things. So let's take a look at an example. So if x is Poisson, you have one parameter, L is 1. So your first moment is just lambda. If x is gamma, you have two parameters, r and lambda. So L is 2, and you can write formulas for your moments in terms of your parameters. Step 2 is you use algebra to invert your system of equations so that instead of writing moments in terms of parameters, you're writing parameters in terms of moments. I give you the examples for Poisson and gamma. And then finally, for step 3, now that we have our parameters as functions of moments, we estimate the moments using your data. So the estimator for the moments are sample moments, which in the homework you'll show is an unbiased estimator for the moments. And so I provide you an example here. So that was today's Whirlwind class. Another great Wednesday.